We're looking here at a sequence a sub n is equal to 3 plus 5n squared over 1 plus n, and we're asked if this sequence converges or diverges, and if it does converge, to find the limit. Since convergence or divergence is about a limit, we're going to start there. The limit as n approaches infinity of 3 plus 5n squared divided by 1 plus n is a lot like a limit at infinity that you would have seen in an earlier chapter. In such cases, I divide the numerator and denominator by the largest power of the variable that appears in the denominator. So in this case, I'm going to multiply numerator and denominator by 1 over n. We get the limit as n approaches infinity of 3 over n plus 5n divided by 1 over n plus 1. Both of the terms with n in their denominators will become 0, and we end up with the limit as n approaches infinity of 5n. Well, as n approaches infinity, 5n approaches infinity, the limit is infinity. We then say the sequence diverges. Next up, same instructions. The sequence is a sub n is equal to 4 to the n over 1 plus 9 to the n. The first thing I'd like to do is note that 1 plus 4 to the n over 9 to the n is positive. Next, I'd like to point out that 4 to the n over 1 plus 9 to the n is less than 4 to the n over 9 to the n because 1 plus 9 to the n is a larger denominator and therefore yields a smaller result. So we can say that 4 to the n over 1 plus 9 to the n is between 0 and 4 to the n over 9 to the n. While we've developed this as strict inequalities, it's not incorrect to say that they're non-strict inequalities. If 0 is less than 4 to the n over 1 plus 9 to the n, then 0 is less than or equal to 4 to the n over 1 plus 9 to the n. Likewise, the other inequality. Considering 4 to the n over 9 to the n as 4/9 to the n, I'm now going to make another note. The limit as n approaches infinity of r to the n is equal to 0 if r is between -1 and 1, strict inequalities, and it's equal to 1 if r is equal to 1. Both of these instances mean convergent, and the limit is divergent otherwise. It follows that the limit as n approaches infinity of 4/9 to the n is equal to 0. So we have the limit as n approaches infinity of 0 is less than or equal to the limit as n approaches infinity of 4 to the n over 1 plus 9 to the n, which is less than or equal to the limit as n approaches infinity of 4 to the n over 9 to the n. Since the limit on the left is 0 and the limit on the right is 0, it follows that the limit in the middle as n approaches infinity of 4 to the n over 1 plus 9 to the n is equal to 0 by the squeeze theorem. And just to put a little underscore on it, that means that the sequence is convergent. Here we used the squeeze theorem. There's an alternative way to do this. We could have said, starting with 4 to the n over 1 plus 9 to the n, that we can divide by the largest base with the exponent that shows up in the denominator. So in the numerator, 1 over 9 to the n, and in the denominator, multiply by 1 over 9 to the n. We end up with, in the numerator, 4/9 to the n, and in the denominator, 1 over 9 to the n plus 1. And the limit as n approaches infinity of 4/9 to the n over 1/9 to the n plus 1, well, it's got a term in the numerator with a base less than 1. That goes to 0. And in the denominator, 1/9 to the n goes to 0. So we end up with an answer of 0. That shouldn't be pink. We would again conclude that the sequence is convergent. Let's look at one more. a sub n is equal to e to the 2n divided by n plus 2. Let's focus on the exponent. The limit as n approaches infinity of the exponent 2n over n plus 2 is handled by dividing by the largest power of n that appears in the denominator. So that becomes the limit as n approaches infinity of 2 over 1 plus 2 over n by multiplying the numerator and denominator by 1 over n. Of course, the 2 over n as n approaches infinity goes to 0. And so we get an answer of 2 for the exponent. What we just used here is a theorem that says that if the limit as x approaches infinity of f of x is equal to L, and if f of n is equal to a sub n, when n is an integer, then the limit as n approaches infinity of a sub n is equal to L. And we didn't just use it here. We've used it in a couple of the previous examples. The difference between f of x and a sub n, it looks like it's just x versus n, but theoretically the difference is that f of x is generally a function that is the graph of which is a curve, whereas a sub n, while it's a function, the graph would be a set of points. Its domain is a bunch of just discrete input values. And what we just used was the idea that 2x over x plus 2 would be the f of x. But then expressing that as a sequence with a bunch of discrete input values doesn't change the limit. That's what this theorem says. We're going to bring this one home by looking at one more theorem. If the limit as n approaches infinity of a sub n is equal to L, so if a sequence has a limit, and if the function f is continuous at L, then the limit as n approaches infinity of f of a sub n is equal to f of L. Now we're looking at this through the lens that f of x is equal to e to the x, and a sub n is equal to n over n plus 2, 2n over n plus 2. You're going to say, you just told me that was 2x over x plus 2 a minute ago. I know, but that was so we could find its limit. Now we're moving on. Now we're going to consider the whole thing, right? E to the exponent. And we just found that the limit as n approaches infinity of 2n over n plus 2 is equal to 2. Therefore, the limit as n approaches infinity of e to the 2n over n plus 2 is equal to e to the 2, the limit of the sequence. Essentially, a limit will pass through a continuous function. And then the limit of a non-continuous function is the same as the limit of the continuous function. That kind of brings it all together there. And the bottom line here is that the sequence is convergent.